CH.3b. Effects of weather on small unmanned aircraft performance. Introduction. This chapter discusses the factors that affect aircraft performance, which include the aircraft weight, atmospheric conditions, runway environment, and the fundamental physical laws governing the forces acting on an aircraft. Since the characteristics of the atmosphere have a major effect on performance, it is necessary to review two dominant factors, pressure and temperature. Density altitude, the more appropriate term for correlating aerodynamic performance in the non-standard atmosphere, is density altitude, the altitude in the standard atmosphere corresponding to a particular value of air density. As the density of the air increases, lower density altitude, aircraft performance increases. Conversely, as air density decreases, higher density altitude, aircraft performance decreases. A decrease in air density means a high density altitude. An increase in air density means a lower density altitude. Density altitude has a direct effect on aircraft performance. Air density is affected by changes in altitude, temperature, and humidity. High density altitude refers to thin air, while low density altitude refers to dense air. The conditions that result in a high density altitude are high elevations, low atmospheric pressures, high temperatures, high humidity, or some combination of these factors. Lower elevations, high atmospheric pressure, low temperatures, and low humidity are more indicative of low density altitude. Effects of pressure on density. Since air is a gas, it can be compressed or expanded. When air is compressed, a greater amount of air can occupy a given volume. Conversely, when pressure on a given volume of air is decreased, the air expands and occupies a greater space. That is, the original column of air at a lower pressure contains a smaller mass of air. In other words, the density is decreased. In fact, density is directly proportional to pressure. If the pressure is doubled, the density is doubled, and if the pressure is lowered, so is the density. This statement is true only at a constant temperature. Effects of temperature on density. Increasing the temperature of a substance decreases its density. Conversely, decreasing the temperature increases the density. Thus, the density of air varies inversely with temperature. This statement is true only at a constant pressure. In the atmosphere, both temperature and pressure decrease with altitude and have conflicting effects upon density. However, the fairly rapid drop in pressure as altitude is increased usually has the dominant effect. Hence, pilots can expect the density to decrease with altitude. Effects of humidity, moisture, on density. The preceding paragraphs are based on the presupposition of perfectly dry air. In reality, it is never completely dry. The small amount of water vapor suspended in the atmosphere may be negligible under certain conditions, but in other conditions humidity may become an important factor in the performance of an aircraft. End of page 21. Water vapor is lighter than air, consequently, moist air is lighter than dry air. Therefore, as the water content of the air increases, the air becomes less dense, increasing density altitude and decreasing performance. It is lightest or least dense when, in a given set of conditions, it contains the maximum amount of water vapor. Humidity, also called relative humidity, refers to the amount of water vapor contained in the atmosphere and is expressed as a percentage of the maximum amount of water vapor the air can hold. This amount varies with the temperature. Warm air can hold more water vapor, while colder air can hold less. Perfectly dry air that contains no water vapor has a relative humidity of 0%, while saturated air that cannot hold any more water vapor has a relative humidity of 100%. Humidity alone is usually not considered an essential factor in calculating density altitude and aircraft performance, however, it does contribute. Performance. Performance is a term used to describe the ability of an aircraft to accomplish certain things that make it useful for certain purposes. The primary factors most affected by performance are the takeoff and landing distance, rate of climb, ceiling, payload, range, speed, maneuverability, stability, and fuel economy. Climb performance factors. Since weight, altitude, and configuration changes affect excess thrust and power, they also affect climb performance. Climb performance is directly dependent upon the ability to produce either excess thrust or excess power. Weight has a very pronounced effect on aircraft performance. If weight is added to an aircraft, it must fly at a higher angle of attack, AOA, to maintain a given altitude and speed. This increases the induced drag of the wings, as well as the parasite drag of the aircraft. Increased drag means that additional thrust is needed to overcome it, which in turn means that less reserve thrust is available for climbing. Aircraft designers go to great lengths to minimize the weight, since it has such a marked effect on the factors pertaining to performance. A change in an aircraft's weight produces a twofold effect on climb performance. An increase in altitude also increases the power required and decreases the power available. Therefore, the climb performance of an aircraft diminishes with altitude. Measurement of atmosphere pressure. To provide a common reference, the International Standard Atmosphere, ISA, has been established. These standard conditions are the basis for most aircraft performance data. Standard sea level pressure is defined as 29.92 Hg and a standard temperature of 59 degrees Fahrenheit 15 degrees Celsius. Atmospheric pressure is also reported in millibars, MB. With 1 Hg equal to approximately 34 MB, standard sea level pressure is 1013.2 MB. Typical MB pressure readings range from 950.0 to 1040.0 MB. Surface charts, high and low pressure centers, and hurricane data are reported using MB. Since weather stations are located around the globe, all local barometric pressure readings are converted to a sea level pressure to provide a standard for records and reports. To achieve this, each station converts its barometric pressure by adding approximately 1 Hg for every 1,000 feet of elevation. End of page 22. For example, a station at 5,000 feet above sea level, with a reading of 24.92 Hg, reports a sea level pressure reading of 29.92 Hg. By tracking barometric pressure trends across a large area, weather forecasters can more accurately predict movement of pressure systems and the associated weather. For example, tracking a pattern of rising pressure at a single weather station generally indicates the approach of fair weather. Conversely, decreasing or rapidly falling pressure usually indicates approaching bad weather and, possibly, severe storms. Effect of obstructions on wind. Another atmospheric hazard exists that can create problems for pilots. Obstructions on the ground affect the flow of wind and can be an unseen danger. Ground topography in large buildings can break up the flow of the wind and create wind gusts that change rapidly in direction and speed. These obstructions range from man-made structures, like hangars, to large natural obstructions, such as mountains, bluffs, or canyons. The intensity of the turbulence associated with ground obstructions depends on the size of the obstacle and the primary velocity of the wind. This can affect the performance of any aircraft and can present a very serious hazard. This same condition is even more noticeable when flying in mountainous regions. Figure 3.3. While the wind flows smoothly up the windward side of the mountain and the upward currents help to carry an aircraft over the peak of the mountain, the wind on the leeward side does not act in a similar manner. As the air flows down the leeward side of the mountain, the air follows the contour of the terrain and is increasingly turbulent. This tends to push an aircraft into the side of a mountain. The stronger the wind, the greater the downward pressure and turbulence become. Low-level wind shear. Wind shear is a sudden, drastic change in wind speed and/or direction over a very small area. Wind shear can subject an aircraft to violent updrafts and downdrafts, as well as abrupt changes to the horizontal movement of the aircraft. While wind shear can occur at any altitude, low-level wind shear is especially hazardous due to the proximity of an aircraft to the ground. Low-level wind shear is commonly associated with passing frontal systems, thunderstorms, temperature inversions, and strong upper-level winds, greater than 25 knots. End of page 23. Wind shear is dangerous to an aircraft. It can rapidly change the performance of the aircraft and disrupt the normal flight attitude. For example, a tailwind quickly changing to a headwind causes an increase in airspeed and performance. Conversely, a headwind changing to a tailwind causes a decrease in airspeed and performance. In either case, a pilot must be prepared to react immediately to these changes to maintain control of the aircraft. The most severe type of low-level wind shear, a microburst, is associated with convective precipitation into dry air at cloud base. Microburst activity may be indicated by an intense rain shaft at the surface, but virga at cloud base and a ring of blowing dust is often the only visible clue. A typical microburst has a horizontal diameter of 1 to 2 miles and a nominal depth of 1,000 feet. The lifespan of a microburst is about 5 to 15 minutes, during which time it can produce downdrafts of up to 6,000 feet per minute (FPM) and headwind losses of 30 to 90 knots, seriously degrading performance. It can also produce strong turbulence and hazardous wind direction changes. During an inadvertent microburst encounter, the small UA may first experience a performance-increasing headwind, followed by performance-decreasing downdrafts, followed by a rapidly increasing tailwind. This can result in terrain impact or flight dangerously close to the ground. An encounter during approach involves the same sequence of wind changes and could force the small UA to the ground short of the intended landing area. It is important to remember that wind shear can affect any flight at any altitude. While wind shear may be reported, it often remains undetected and is a silent danger to aviation. Always be alert to the possibility of wind shear, especially when flying in and around thunderstorms and frontal systems. Atmospheric stability. The stability of the atmosphere depends on its ability to resist vertical motion. A stable atmosphere makes vertical movement difficult, and small vertical disturbances dampen out and disappear. In an unstable atmosphere, small vertical air movements tend to become larger, resulting in turbulent airflow and convective activity. Instability can lead to significant turbulence, extensive vertical clouds, and severe weather. The combination of moisture and temperature determine the stability of the air and the resulting weather. Cool, dry air is very stable and resists vertical movement, which leads to good and generally clear weather. The greatest instability occurs when the air is moist and warm, as it is in the tropical regions in the summer. Typically, thunderstorms appear on a daily basis in these regions due to the instability of the surrounding air. Inversion. As air rises and expands in the atmosphere, the temperature decreases. There is an atmospheric anomaly that can occur, however, that changes this typical pattern of atmospheric behavior. When the temperature of the air rises with altitude, a temperature inversion exists. Inversion layers are commonly shallow layers of smooth, stable air close to the ground. The temperature of the air increases with altitude to a certain point, which is the top of the inversion. The air at the top of the layer acts as a lid, keeping weather and pollutants trapped below. If the relative humidity of the air is high, it can contribute to the formation of clouds, fog, haze, or smoke, resulting in diminished visibility in the inversion layer. Surface-based temperature inversions occur on clear, cool nights when the air close to the ground is cooled by the lowering temperature of the ground. The air within a few hundred feet of the surface becomes cooler than the air above it. Frontal inversions occur when warm air spreads over a layer of cooler air, or cooler air is forced under a layer of warmer air. End of page 24. Temperature/dew point relationship. The relationship between dew point and temperature defines the concept of relative humidity. The dew point, given in degrees, is the temperature at which the air can hold no more moisture. When the temperature of the air is reduced to the dew point, the air is completely saturated and moisture begins to condense out of the air in the form of fog, dew, frost, clouds, rain, or snow. Methods by which air reaches the saturation point. If air reaches the saturation point while temperature and dew point are close together, it is highly likely that fog, low clouds, and precipitation will form. There are 4 methods by which air can reach the saturation point. First, when warm air moves over a cold surface, the air temperature drops and reaches the saturation point. Second, the saturation point may be reached when cold air and warm air mix. Third, when air cools at night through contact with the cooler ground, air reaches its saturation point. The fourth method occurs when air is lifted or is forced upward in the atmosphere. Dew and frost. On cool, clear, calm nights, the temperature of the ground and objects on the surface can cause temperatures of the surrounding air to drop below the dew point. When this occurs, the moisture in the air condenses and deposits itself on the ground, buildings, and other objects like cars and aircraft. This moisture is known as dew and sometimes can be seen on grass and other objects in the morning. If the temperature is below freezing, the moisture is deposited in the form of frost. While dew poses no threat to a small UA, frost poses a definite flight safety hazard. Frost disrupts the flow of air over the wing and can drastically reduce the production of lift. It also increases drag, which when combined with lowered lift production, can adversely affect the ability to take off. A small UA must be thoroughly cleaned and free of frost prior to beginning a flight. Clouds. To pilots, the cumulonimbus cloud is perhaps the most dangerous cloud type. It appears individually or in groups and is known as either an air mass or orographic thunderstorm. Heating of the air near the Earth's surface creates an air mass thunderstorm. The upslope motion of air in the mountainous regions causes orographic thunderstorms. Cumulonimbus clouds that form in a continuous line are non-frontal bands of thunderstorms or squall lines. Since rising air currents cause cumulonimbus clouds, they are extremely turbulent and pose a significant hazard to flight safety. For example, if a small UA enters a thunderstorm, the small UA could experience updrafts and downdrafts that exceed 3,000 fpm. In addition, thunderstorms can produce large hailstones, damaging lightning, tornadoes, and large quantities of water, all of which are potentially hazardous to an aircraft. Standing lenticular altocumulus clouds. Standing lenticular altocumulus clouds are formed on the crests of waves created by barriers in the wind flow. The clouds show little movement, hence the name standing. Wind, however, can be quite strong blowing through such clouds. They are characterized by their smooth, polished edges. The presence of these clouds is a good indication of very strong turbulence and should be avoided. End of page 25. Stability of an air mass determines its typical weather characteristics. When one type of air mass overlays another, conditions change with height. Characteristics typical of an unstable and a stable air mass are as follows. Reference image. Fronts. As air masses move out of their source regions, they come in contact with other air masses of different properties. The zone between two different air masses is a frontal zone or front. Across this zone, temperature, humidity, and wind often change rapidly over short distances. Mountain flying. When planning a flight over mountainous terrain, gather as much pre-flight information as possible on cloud reports, wind direction, wind speed, and stability of air. Satellites often help locate mountain waves. Adequate information may not always be available, so remain alert for signposts in the sky. Wind at mountain top level in excess of 25 knots suggests some turbulence. Wind in excess of 40 knots across a mountain barrier dictates caution. Stratified clouds mean stable air. Standing lenticular and/or rotor clouds suggest a mountain wave. Expect turbulence many miles to the lee of mountains and relative smooth flight on the windward side. Convective clouds on the windward side of mountains mean unstable air. Expect turbulence in close proximity to and on either side of the mountain. Structural icing. Two conditions are necessary for structural icing in flight. 1. The aircraft must be flying through visible water such as rain or cloud droplets. 2. The temperature at the point where the moisture strikes the aircraft must be 0 degrees Celsius or colder. Aerodynamic cooling can lower temperature of an airfoil to 0 degrees Celsius even though the ambient temperature is a few degrees warmer. Thunderstorm life cycle. A thunderstorm cell during its life cycle progresses through 3 stages: 1. The cumulus, 2. The mature, and 3. The dissipating. It is virtually impossible to visually detect the transition from one stage to another. The transition is subtle and by no means abrupt. Furthermore, a thunderstorm may be a cluster of cells in different stages of the life cycle. The cumulus stage. Although most cumulus clouds do not grow into thunderstorms, every thunderstorm begins as a cumulus. The key feature of the cumulus stage is an updraft as illustrated in Figure 3.4. The updraft varies in strength and extends from very near the surface to the cloud top. Growth rate of the cloud may exceed 3,000 feet per minute, so it is inadvisable to operate a small UA in an area of rapidly building cumulus clouds. End of page 26. Early during the cumulus stage, water droplets are quite small but grow to raindrop size as the cloud grows. The upwelling air carries the liquid water above the freezing level, creating an icing hazard. As the raindrops grow still heavier, they fall. The cold rain drags air with it, creating a cold downdraft coexisting with the updraft. The cell has reached the mature stage. The mature stage precipitation beginning to fall from the cloud base is your signal that a downdraft has developed and a cell has entered the mature stage. Cold rain in the downdraft retards compressional heating, and the downdraft remains cooler than surrounding air. Therefore, its downward speed is accelerated and may exceed 2,500 feet per minute. The down-rushing air spreads outward at the surface as shown in Figure 3.4, producing strong, gusty surface winds, a sharp temperature drop, and a rapid rise in pressure. The surface wind surge is a plow wind and its leading edge is the first gust. Meanwhile, updrafts reach a maximum with speeds possibly exceeding 6,000 feet per minute. Updrafts and downdrafts in close proximity create strong vertical shear and a very turbulent environment. All thunderstorm hazards reach their greatest intensity during the mature stage. The dissipating stage. Downdrafts characterize the dissipating stage of the thunderstorm cell as shown in Figure 3.4, and the storm dies rapidly. When rain has ended and downdrafts have abated, the dissipating stage is complete. When all cells of the thunderstorm have completed this stage, only harmless cloud remnants remain. Ceiling. For aviation purposes, a ceiling is the lowest layer of clouds reported as being broken or overcast, or the vertical visibility into an obscuration like fog or haze. Clouds are reported as broken when 5/8 to 7/8 of the sky is covered with clouds. End of page 27. Overcast means the entire sky is covered with clouds. Current ceiling information is reported by the Aviation Routine Weather Report, METR, and automated weather stations of various types. Visibility. Closely related to cloud cover and reported ceilings is visibility information. Visibility refers to the greatest horizontal distance at which prominent objects can be viewed with the naked eye. Current visibility is also reported in METR and other aviation weather reports, as well as by automated weather systems. Visibility information, as predicted by meteorologists, is available for a pilot during a pre-flight weather briefing. End of page 28. End of chapter 3b. If you liked this video, please like, share, and subscribe. Thank you.